Welcome to today's deep dive. We're going to be exploring direct conversion nuclear reactors.
Oh, wow.
These are the ones that could maybe even surpass the efficiency of those huge steam turbine systems that we've, relied on for so long.
Yeah, there's massive things.
Exactly. And to do that, we're going to be taking a really close look at a proposal from N5 Digital Inc. This is from January 3rd, 2025.
Okay.
And it's all about the technical feasibility of these reactors.
Sounds pretty dense.
It is.
I like it.
Yeah, well, this proposal, it really zeroes in on the science.
Okay.
It's got this really cool collaborative research plan between U.S. and Israeli teams.
Nice.
And they're basically trying to answer one question. Can these new direct conversion technologies that they're proposing be scaled up to produce megawatts of power?
So, before we even, start thinking about, the societal impacts or the economics.
Exactly. We've got to nail down. Can we even do this question first?
Okay, so this is, strictly a technical deep dive.
For now, at least.
All right, I can dig it up.
Cool. So they're looking at two main technologies here. Heat to light to electricity conversion, or HLEC.
Catchy.
Yeah. And then there's thermophotovoltaic conversion.
Is there, a shorter name for that?
Yeah. We'll just call it TPV for short.
Okay.
So TPV it is.
Gotcha.
Both of these are based on a pretty, basic but elegant idea.
Mm-hmm.
Converting heat directly into electricity.
Straight up, no middleman.
Exactly.
Cool.
So HLEC uses these special materials that give off light when they heat up.
Ah, okay.
Kind of like a light bulb, but way more advanced.
Yeah, a little bit more complicated than your average light bulb.
For sure. And then they use photovoltaic cells to convert that light into electricity.
It's like solar panels.
Pretty much.
Got it.
Okay, so what about TPV? Is that similar?
Yeah, it is. It uses the same basic principle, but it's even more, I guess you could say, targeted.
Okay.
It focuses on a very specific infrared spectrum to try and squeeze out even more efficiency.
Yeah. So it's like they're fine-tuning it to capture as much energy as possible.
Exactly. It's all about optimization.
Now, it sounds amazing on paper.
Right.
But I imagine there are some major challenges.
Yeah.
We're talking about the inside of a nuclear reactor, right?
Oh, yeah.
That's got to be tough.
You're telling me.
So what are the biggest hurdles here?
I think the biggest one, and they acknowledge this right up front, is the whole materials science side of things.
Okay.
You need materials that can handle the crazy temperatures inside a reactor, but also can withstand, being bombarded by radiation all the time.
So they have to be tough.
Oh, yeah. Super tough.
Not easy to find stuff like that.
Not at all. Finding the right materials is going to make or break this whole project.
So what are they proposing to do about that?
Well, they've laid out a very systematic 3-phase research plan.
Okay.
It's all about tackling this materials challenge head on.
Nice.
So the first phase is all about the foundational research.
Right. Back to basics.
Yeah. They're going to be doing a lot of theoretical analysis, carefully selecting materials and running tons of computer simulations to try and figure out what the best spectral ranges are and the best materials for both HLEC and TPV.
So it sounds like they're really doing their homework in this first phase.
Oh, yeah.
Laying the groundwork.
For sure.
So what happens after they have a better grasp of the theory and the material?
That takes us to phase 2, experimental validation.
Okay.
This is where theory meets reality.
Love it.
They're going to be building prototype thermal emitters and testing out different photovoltaic cell materials.
Putting it to the test.
Exactly, to see how they perform in real-world conditions.
Mm-hmm.
And get this. They're even planning to build a small-scale demonstrator just to prove that the concept actually works.
So a mini version of the real thing?
Yeah, a proof of concept.
Before they go big.
Exactly. It's a crucial step to attract more investment and show that scaling up to megawatts is a realistic goal.
Makes sense. But even then, a short-term win doesn't guarantee, long-term success.
You're absolutely right.
So what's phase 3 all about?
Phase 3 is all about the feasibility of scaling.
So this is where they figure out if it can actually go the distance.
Exactly. Phase 3 is all about long-duration testing.
Okay.
They're going to be checking how well everything holds up over time, looking for any signs of, material degradation or unexpected inefficiencies that might pop up after extended use. They'll also be working on a conceptual design for a direct conversion reactor that could actually produce megawatts of power.
So taking that small-scale demonstrator and figuring out how to make it into a real power-generating reactor.
Yeah, that's a pretty big leap.
It is. And to tackle this challenge, they're proposing a collaboration between top U.S. nuclear experts and scientists from the Technion Israel Institute of Technology.
Okay.
Have you heard of Technion?
Oh, yeah, they've got a great reputation.
They do. They're known for their expertise in advanced materials, photonics, and nanotechnology.
all essential for this project.
All crucial stuff. Yeah, so they're bringing together the best of both worlds. American nuclear know-how with Israeli expertise in these cutting-edge fields.
Smart.
But all of this research can't be cheap.
No way.
What's the budget looking like?
They've estimated somewhere between $50 and $75 million over 3 to 5 years.
Wow, that's a lot of money.
It is. But if this technology works, the payoff could be huge.
Yeah, I mean, it could be game-changing, but at least they've got a plan for where the money's going to go.
Yeah, absolutely. The proposal breaks down exactly how the funding would be used in each phase, like all the resources they need for research materials, equipment, and personnel.
So it's all there in black and white.
Yeah, it's really detailed, which I appreciate.
Yeah, it shows that they're really serious about this.
Exactly. They understand the challenges, and they're being transparent about it.
That's good to hear, especially with something this complex and potentially revolutionary.
Yeah.
So we talked about the importance of materials, but what are some of the other technical challenges they got to overcome?
Well, one of the big ones is figuring out the design of the reactor core itself.
Oh, right. So it's not just about making heat. It's about making heat that works with these new HLEC and TPV systems.
Exactly. They need to make sure that the heat output from the core is perfectly matched to what those systems need.
Kind of like designing a stovetop that's made for a specific type of pot.
Yeah, that's a great analogy.
You need the right amount of heat in the right places.
Exactly. And then there's the big issue of radiation.
Right. Even if they find materials that can take the heat, they got to make sure they don't fall apart from all the radiation.
Yeah, they got to last for years of continuous operation, not just a few months.
So these materials got to be super resilient.
Yeah, it's a tough environment.
That's where the tech team comes in, right?
Absolutely. They're the experts when it comes to developing radiation-resistant materials.
Mm-hmm.
They've got a lot of experience in this area.
What kind of materials are they looking at?
They're considering things like refractory metals and ceramics for the thermal emitters. Those materials have really high melting points and can withstand extreme conditions.
Sounds pretty hardcore.
Oh, yeah, they're tough stuff. But what about the photovoltaic cells on the other side?
Yeah, those have to be radiation hardened too, right?
Of course, it's a challenge on both ends.
What?
They're exploring materials like gallium antimonide and gallium arsenide, which are known for being good at converting specific wavelengths of light into electricity.
Okay.
But the really exciting part is that they're not just sticking to what we already have. They're actively researching new photovoltaic materials that could be even better.
So they're really pushing the boundaries here.
Oh, yeah. Trying to find the best possible solutions for both ends of the conversion process.
That's amazing.
Yeah.
But even if they find the perfect materials, they still have to figure out how to get all that heat from the core to those thermal emitters.
Yeah, that's another big engineering challenge, designing the most efficient plumbing system in the world for super intense heat.
I can't even imagine.
They're looking at technologies like heat pipes and molten salt loops, things that have been used in other high-temperature applications.
So they're borrowing from other fields.
Exactly. The goal is to move that heat with as little energy loss as possible, so it all reaches those thermal emitters where it can be converted into light.
So you got to find the right materials, design a reactor core that works perfectly with HLEC and TPV, and then figure out how to move all that heat around without losing any of it.
Yeah, and we haven't even talked about scaling everything up.
Right. Can they take what they've learned in the lab and make it work on a massive scale?
That's the million-dollar question, and that's where the system integration modeling in Phase 3 comes in.
Right.
We're going to be creating these really complex simulations to see how a full-scale HLEC or TPV system would actually work inside a real reactor.
So it's like going from a model airplane to a real jumbo jet.
Yeah. There's a huge difference in complexity. They have to consider things like the layout of the emitters and photovoltaic cells, how the heat flows, how to manage all the electricity that's generated, and so much more.
Sounds like a massive undertaking.
Oh, yeah, it is. But if they can pull it off, the impact could be huge.
In what way?
Well, from a technical standpoint, it could mean smaller, more efficient reactors that produce way more power from the same amount of nuclear fuel.
So it's not just about doing what we're doing now, but doing it better.
Exactly, and that could lead to lower costs and maybe even open up new possibilities for nuclear power in places where traditional reactors just wouldn't work.
That's pretty incredible. But beyond the technical stuff, what about the bigger picture? How could this research change the way we think about nuclear energy?
That's a question for another deep dive.
Okay, fair enough.
Right now, we're focused on the technical side. Can this technology actually do what they're claiming?
Makes sense. And based on this proposal, it seems like it's worth exploring.
I think so too, but it all comes down to funding.
Yeah. Who's going to pay for all of this?
Well, that's where things get even more interesting. So they've got this really ambitious plan, a top-notch team, and a clear vision for the future of nuclear energy. But the big question is, who's going to pay for it all?
That is the question, isn't it? I mean, it's got to cost a fortune.
Well, they're not putting all their eggs in one basket, that's for sure. They've got a multi-pronged funding strategy lined up. They're looking at government agencies, private investors, even international collaborations.
So they're hoping someone will bite.
Yeah, basically. But they're not just sending out random requests. They've actually identified some very specific potential funding sources.
Oh, okay. So who are they thinking?
Well, on the government side, they're looking at the U.S. Department of Energy.
Makes sense.
They're always interested in new clean energy technologies. And they're also thinking about the National Science Foundation. You know, they fund a lot of groundbreaking research.
Yeah, across all sorts of fields.
Exactly. So those are the main government targets.
Okay, but what about private investors? Would venture capitalists really be interested in something like this? I mean, nuclear reactor research is pretty long-term and complex.
It might seem like a long shot, but there's actually a growing trend of private investment in clean energy tech, especially stuff that has the potential for big returns. And this isn't just about making things a little bit better. This research could completely revolutionize the nuclear industry.
So the potential payoff is huge.
Exactly. And that kind of game-changing potential could definitely attract investors who are willing to take a chance.
So it's not just about saving the world. It's about making money while you do it.
Yeah, basically. But they're not just relying on U.S. funding either. They're also looking at international collaborations.
Okay. And why would other countries want to get involved?
Well, everyone wants clean and efficient energy.
That's true.
A lot of countries are trying to get away from fossil fuels and move towards more sustainable energy sources.
Right.
And remember, Israel is a big part of this collaboration. They bring a lot of expertise in advanced materials and nanotechnology.
So it's a win-win for everyone involved.
So they've got a plan, a great team, and a diverse funding strategy. What do you think are the chances that this research actually happens?
It's hard to say for sure, but I'd say they have a pretty good shot.
Yeah.
Yeah, this proposal is really well put together. They've identified a real problem, proposed a solution that could actually work, and they've got the team and resources to make it happen.
So it's a gamble, but a smart one.
I think so.
If it works, what could this mean for the future of nuclear energy?
Well, that's a question we can explore in more detail in a future deep dive.
Okay, fair enough.
But I think it's safe to say that direct conversion nuclear reactors have the potential to be a real game changer. If they can achieve the kind of efficiency and safety that they're talking about in this proposal, it could change everything.
Wow, that's pretty exciting stuff.
It is. It really shows what's possible when people put their minds together and come up with innovative solutions.
Absolutely. Well, I think that wraps up our deep dive into the technical side of direct conversion nuclear reactors. Yeah, I think we covered it all.
It's been a fascinating look at a potentially revolutionary technology. We'll keep you updated on the progress of this research and explore some of the bigger implications in future episodes.
Sounds good.
Thanks for joining us on this deep dive.